from yesterday's lecture. We wrote actually the Hamiltonian. Okay, if your magnetic field is oriented along z direction, okay, then I can write the spin half particle like this. Okay, so this is the Hamiltonian for the spin half particle oriented along z direction. Clear? Got it? So now let's look the time evolution. Okay, so let's look at the time evolution operator. So how time evolution operator looks like? Okay, if you are there are two ways to study the dynamics: either directly look at the Schrodinger equation or look at the time evolution operator. They are one and the same things. Okay, so you either look at the you solve a time dependent Schrodinger equation that's equivalent to saying you figure out a time evolution operator. Clear? Okay, so let's write that time evolution operator. You start from some initial time to some t. So this is always written as, so if our Hamiltonian is independent of time, so it is written like this thing. Okay, so this is our time evolution operator. Clear? So now this I can write as e raised power minus I. What is h? Omega. Okay, as zt by h. Clear? Got it? Okay. So now if you look here, so I can put, let's write this, I can put this omega t as phi. Okay, so let's write it as e raised power minus I as z phi by h trans. What is our phi? Omega t. So that means if you look at the rotation operator, rotation in xy plane, clear? So your time evolution is of the same nature, and now the angle is what? Given by the omega t. Got it? Okay, so you so now you can get the idea what we are trying to do. So this magnetic, the external magnetic field, okay, when you look at the time evolution of, let's say, the vector, okay, so it will simply make it to precess about the z-axis. Got it? Okay, so what will be now? Let's write. So these average values now I can write these. I can write it as time dependent like this thing. Sx at t equal to 0. So cosine of phi. What is phi? Omega t. So this we have already figured out. Okay. Minus sy. Okay. T equal to 0. Initial. Why I have put explicitly t equal to 0 here? It means the initial average values. Got it? Okay. Then you are having sine of omega t. We have calculated for an angle phi. And now angle phi is what? It is given by omega t. And similarly, you are having syt. So what is that equal to? Sx t equal to 0 sine of omega t plus sy t equal to 0 cosine of omega t. So you are having sz of t. So that is simply as sz equal to 0. Got it? Samajh? Okay. Now let's take this value. Okay. So let's let's make a picture. So it is something, suppose you are having a spin half particle here. Got it? And you apply now the external magnetic field along z direction. So you are having a constant magnetic field along z direction. Okay? So you describe these average values by a vector. Got it? So let's write that vector as, okay, so you are having this kind of vector. Okay? So let's call this vector as V. Its components are what? Average value of Sx, average value of Sy, average value of Sz. Got it? So when you apply now the magnetic field, what will happen? So the tip of the vector will rotate in the xy plane or about the z-axis. Let's say this is your z-axis, this is your y-axis, and this is your x-axis. Okay? So what will happen? So it will just rotate about this axis. So we call this rotation as a precession. Got it? So it is not at the single point, it is something. So you are having, let's think of an electron in an orbit. So at every point, let's say, so this vector is actually precessing. Yeah? So when it moves, okay, so it is something like this. Okay? Got it? So it is moving in an orbit, but precessing about z-axis. Got it? Okay? Okay, so now let's look at this very vector. So if I take omega t, is equal to 2 pi. Or let's look at after 2 pi by omega time. So let's look at what will happen to this very vector if I make time what? 2 pi by omega. Got it? So now what will happen? So if I put this omega t equal to 2 pi, what I will get? So this is 1. What will happen to this? 0. Okay? So in this case, so sxt, okay, after what 2 pi by omega rotation, okay, or after this much of time, what will happen? So you will get back what? T equal to 0, cos the cosine of this thing 1. What is sy? Now tell me. So you will get back what? Sy. Because this will be 0. What will about sz? Okay. What about sz? It will go as sz. So that means after a 2 pi rotation, this vector comes back to its own position. Samajh? Now yesterday what we have studied? That is actually for a state vector. If you are having a state function, okay, the wave function of a spin half particle returns back to its original position only after what? 4 pi rotation. But here it will rotate the vector, since this is a classical vector, okay, so this will come back only after what? 2 pi rotations. Clear? So this is a very important difference. Okay, so let me write it this way. So this scale gives me a time scale for the precision, because this is actually the precision of the vector, okay, due to the external magnetic field. So I can write it. Okay, so here, okay, you can look that state vector from the time evolution perspective as well. Okay, so let me write. So what is our alpha? So that is c plus c minus minus. So this is our state vector. So let's look at from this very perspective. Then I will put a remark. Okay. Okay. So now let's evolve it in time. So what will happen? So it will go as alpha t e raised power minus iht by h trans acting on alpha. So this is the time evolution ket. Okay. So this is our, in other words, this is the state vector picking up the time evolution. Okay, because of this external magnetic field. So what is this time evolution operator? E raised power minus I as z omega t by h trans. Okay, this is c plus c minus minus. Got it? So you are having now c plus. So sz will act on plus. So it will give you h trans by 2. So it is simply e raised power minus omega t by 2 plus. Okay. This will yield you minus h trans. So it will be simply e raised power I omega t by h trans. Okay. Clear? Okay. So now let's take, if I take now t equal to 2 pi, okay, 4 pi by omega. Got it? So if you take t equal to 2 pi by omega, it will be e raised power minus I omega. Okay, so this 2 pi, sorry, e raised power minus pi, so that will yield you a minus sign. But if you take 4 pi by omega, so you will see, okay, alpha t at 4 pi by omega, so you will get back as what was at t equal to 0. So you can call this as at t equal to 0. Okay? Samajh? Got it? So now this is the difference. So you are having the precision time. Let me write that. Okay. So t precision. So it takes you 2 pi by omega amount of time to return back to the original position. That means this vector will come back after 2 pi rotation. But the state vector, okay. So let's call this as ts. Okay. So there is a name for it. Okay, okay, so let's put, it takes ts amount of time, okay, for the state vector to come back to its original position. Okay, so these are two important time states. Okay, s means state vector, right? Okay, so any question here?
So precision को हम कैसे समझ सकते हैं in terms of wave packets?
No, I am not considering any kind of wave packet here.
नहीं मैं बोल रहा हूँ सर, इसको हम कैसे कंसिडर मतलब समझ सकते हैं in terms of wave packets, electrons को? precession of electrons.
So, in terms of wave packet, what do you mean by that? It's not a wave packet. So, precession happens to what? Vector. So, what is that vector? So, it means the average value, the vector is described by the average values of the components of the spin operator. Okay, or the angular. You can think simply, forget about spin. You can think of the average values of the angular momentum describes your vector. Or in other words, a vector. So that is processing about that very thing. So it's a number. Okay.
Physically,
It's a. So you think actually it's simply the angular momentum vector which is actually rotating it. It has nothing to do with the wave packet. Okay, it has nothing to do with the wave function of the particle. Okay. So you have done this, let's say LS coupling. You will be doing it in the atomic physics course as well. But I have told you LS coupling or JJ coupling kind of thing, is it? So what does that mean? So because of this precision, there arises this spin orbit coupling. Okay. I have told you in the partition theory when we are doing it. Okay. So look here. What is happening? So think of an electron. Think of the hydrogen atom simply. Okay, you are having one electron there. Okay, and you are having the nucleus. But when you look, if you are an observer as an electron, what you will observe? You will observe the magnetic field generated by the nucleus because nucleus is moving. Okay, it's a electric and magnetic field are the relativistic effects. Yes. Got it? Because of that, what you will see? You will see actually a magnetic field acting on you, and this magnetic field will affect your angular momentum. Clear? Here we have seen it's actually the spin angular momentum. Clear? So it will affect the angular momentum vector. Okay? So that will make it to precess. Okay? And actually that will give rise to the spin orbit coupling, that magnetic field. Here the magnetic field, what I have considered, it is something external. I am not taking that intrinsic magnetic field. Okay? You can consider that intrinsic magnetic field as well. There is no problem. The intrinsic magnetic field generated by the nucleus. Okay? Got it? So, so now let's take, these matrices. Okay. Okay, so let's go back to what we have. Okay, so what we have considered for the spin half. So we have considered these things. So Sx is equal to h cross by 2, 0, 1, 1, 0. Okay. Sy is equal to h cross by 2, 0 minus I 0. And Sz is equal to h cross by 2, 1, 0, 0 minus 1. Clear? Got it? Okay, so we call these, okay, so I can write this as h cross by 2 sigma x. This I can write h cross by 2 sigma y. This I can write it h cross by 2 sigma z. Okay, sigma x, sigma y, sigma z, they are known as Pauli spin matrices. Are called as Pauli spin matrices. Okay? Got it? So therefore, I can write my spin. Let's say the spin operator in general, it's like this thing, h cross by 2 sigma operator for spin half particle. Okay? Or you can put in the index notation SI, ith operator, I can write h cross by 2I, and I is actually equal to x, y, z. Clear? Samajh aa? Okay. So now let's look at the properties of these Pauli spin matrices. Okay, so first property, okay, so they are Hermitian, is that true? Clear? So you just take the dagger, okay, of this 0, 1, 1, 0, so it will be, so that means sigma dagger is same as sigma. So now let's look at the trace of these operators. Let's take trace of sigma x. So what is that equal to? 0. So that is same as trace of sigma y. That is same as trace of sigma z. Clear? So it means they are traceless operators. Got it? समझ रहे हो? Okay. So when you are having traceless operators, so that means you are having equally positive and equally negative eigenvalues. So now let's take this. Okay, so what is sigma x square? So it is, now let's look at the square. So it is 0, 1, okay, 1, 0 multiplied by 0, 1, 1, 0. So what that is? So it is simply identity matrix. Okay, same is true for sigma y square is equal to an identity matrix. Sigma z square is an identity matrix. Got it? Now you are having sigma square is, or I can write like this thing. Sigma square is equal to an identity matrix. Clear? So when you are having square of, if this is an idempotent, so what does it means? It means the eigenvalues has to be plus minus 1. It's a two-dimensional matrix. How many eigenvalues will be there? 2 eigenvalues. Look, the condition says trace is equal to 0. So it means both eigenvalues should be opposite to each other. Clear? This magnitude be same, but sign should be different. Clear? So that trace is equal to 0. So it implies therefore, what are the eigenvalues? So eigenvalues of sigma are plus minus 1. For all sigma x, sigma y, sigma z. Clear? समझ आओ? Okay. So in other words, if I take for spin half particle, that s square. Okay. So s square will be simply h cross square by 4 sigma square. So it implies therefore this s, okay, have, okay, eigenvalues of s are plus minus h cross by 2 for a spin half particle. I am considering only the spin matrices. I am not taking the units. H cross by 2. Okay? Clear? Okay, so now let's look another properties. Okay, so let's take fourth one. So if I take now, let's say sigma x, sigma y, okay, minus, okay, so let's do it from here. So you are having Si, Sj, that's equal to what? I h cross epsilon I j k s a. Clear? Is it?
Yes, sir.
Okay, so what is our Si? It is h cross by 2 sigma I. Means I. Okay, so what are ij? I, j, k. They are actually x, y, z. Are 1, 2, 3. So it is actually equal to h cross by 2 sigma j. So what you are having here? I h cross epsilon I j k h cross by 2 sigma k. Clear? Okay. So you are having h cross square by 4, h cross square by 2. So it implies you are having this very commutator. Sigma I sigma j, it is equal to twice I h cross epsilon I j k sigma. So memorize this thing. Okay? So what it means? So let's take, it means you are having like this thing, sigma x, sigma y commutator. So that's actually sigma x, sigma y minus sigma y, sigma x. So that's equal to twice I h cross. Okay, you put I, okay, x, y. Then this should be z. Clear? So it is simply x, y, z. That's 1. So it is sigma z. Okay, and so on. Got it? Okay. Now if I take, okay, so now let's look the another thing. Okay, so let's take, okay, so let's call this as first. Okay, so I am having this object as well. Let's take, if I take sigma I, sigma j plus sigma j, sigma I, so that's equal to twice delta I j for, okay, okay, so let's put it this way. Clear? What it means? So it means, okay, so what it means for I not equal to j, this is sigma I sigma j plus sigma j sigma I, this is equal to 0. Clear? So this means this is an anti-commutator. So it is an, and you can check it. So let's take, okay, so for example, let me take this way. I is not equal to j. So it means I will take sigma x, sigma y plus sigma y, sigma x. So let's take this thing. So what is sigma x? 0, 1, 1, 0. What is sigma y? 0 minus I, 0. So then you are having plus 0 minus I, 0. Then you are having 0, 1, 1, 0. So you calculate these products, you will get what? 0. So it means sigma x, sigma y anti-commute. So Pauli spin matrix is actually you are having a commutation relation as well as an anti-commutation relation. Clear? समझ आया? So you are having here a commutation relation between Pauli spin matrices. You are also having a anti-commutation relation. So this I can put this very object as like this thing. Memorize these two objects. So it is twice delta I. So these are important. Call this as sects. Okay. Now let's add first and second. Okay. Add first and second. So what it means? So you are having sigma I, sigma j minus sigma j, sigma I. Okay. Then add from here. So you are having sigma I, sigma j plus sigma j, sigma I. So what is that equal to? You are having twice I extras. No, there will be no extras because there is no extras. You are having extra square here, extra square here. Clear? So extra square cancels. Only you are having extra square by 4 actually here. Here you are having extra square by 2. Huh? That's why this 2 is. There is no extras. Huh? So because you don't have they are plain matrices. Huh? You don't have extras anywhere. Huh? Clear? Okay. So it is twice I epsilon I j k sigma k plus twice delta I j. Clear? Just I am adding. So left hand side and then right hand side. So it means this object cancels. Okay. So what you got? Twice sigma I, sigma j. That's equal to twice I. Okay. So let's take 2 out. So I will write this delta ij first. Delta ij plus I epsilon I j k sigma. So what it gives? So which implies sigma I, sigma j is equal to delta ij plus I epsilon I j k sigma. Okay, so this is very important relation. Okay, so there is another objective you can do. You can define ladder operators. Okay, so let's take. Okay, so you are defining this S plus as Sx plus I Sy. Clear? And similarly, S minus you are defining Sx minus ISY. Clear? S plus means spin up, it raises your angular momentum by 1 step, and S minus lowers down your angular momentum by 1 step. Clear? So which implies therefore I can define now this sigma plus and minus, so that I can write sigma x plus minus I sigma y by 2. So this is spin raising and spin lowering operator. So you can write the matrix representation. Okay. So let's write this sigma plus. So that's equal to sigma x plus I sigma y by 2. So how much is that? Half. What is sigma x? 0, 1, 1, 0. Okay. Then you are having plus I. This is equal to 0 minus I 0. Okay. So what that is equal to? So I into this is 1. So it is 2. So it will be simply 0, 1, 0, 0. Similarly, you can have sigma minus is equal to sigma x minus I, sigma y by 2. So that's equal to 0, 1, 0, 0. So these are the matrices corresponding to raising and lowering. Okay, so let's check it. Huh? Okay. Let me give an example. What does that mean? Okay. So how many possible values are here for a spin half particle? 2 values, either up or down. Clear? So what is our up state? So it is 1, 0. And what is our down state? 0, 1. Clear? So if I apply, let's say, S plus on this thing, what it will give me? If I apply sigma plus on this thing, it will raise it to here. Okay, up state. Okay? If I apply sigma minus on this thing, it will lower it down. Clear? Okay, so let's check it. So let's write sigma plus. Okay, so you are having only two possible levels. If I apply sigma plus here, so it will give you 0. If you apply sigma minus here, it will give you 0. But if I apply sigma minus here, it will give you this thing. If I apply sigma plus here, it will give you upper state. Clear? Oh, समझ आओ? Okay. So this will yield you 0. This will also yield you 0. Let's check. Sigma plus acting on this sigma. Okay, so plus. So what is sigma plus? 0, 1, 0, 0. So this is equal to 1, 0. So what that is equal to 0. Clear? So now let's act on sigma minus on this plus. So it is 0, 0, 1, 0 acting on this 0, sorry, 1, 0. So what you get? 0, 1. So what that is equal to? Minus. Clear? Similarly, you can do the other way around. Huh? So you apply sigma minus and then sigma plus. Clear? Okay, so do the rest of the things. So that's why we call sigma plus and sigma minus as raising and lowering operators. Okay? Okay. So now let's look for one more identity. Okay?
Sir, आराम से
Huh?
आराम से
So I have to finish this topic today, huh? Because it's quite simple. Huh? It's simple mathematics. Huh? You don't have to do it think physically. Okay? Clear? So these are simple calculations. I am just giving you the identities. Huh? Nothing more than that. Huh? Okay, so now let's take one more thing. So let's write this objective. Sigma dot A. So what does it mean? So A is a vector. So A is some vector. Okay? What it means? It means it is the projection of the spin angular momentum along A direction. Clear? So it is a projection operator. Clear? So it will give you this kind of operator will measure your spin along the direction of A if A is a vector. Clear? That is how we interpret the dot product. Now if you are having this kind of objective, so this will be frequently used. So I should not put a vector, I should put an operator. So B. So let's say this kind of product you are having. So this will arise kind of frequently. Eh? Okay, so you should know how to evaluate it. Eh? So let's work it out. Then we'll go to the general. Okay, so the general spin along a general direction. So how to do it? Eh? Let's evaluate this very objective. So I will write this as how to write a dot product. I will write summation over I running from 1 to 3 sigma I AI. So this is the dot product. Clear? And then you can write summation j is equal to 1 to 3 sigma j bj. Can I write? Because you are 1 to 3 means x, y, z. Eh? Okay. So this is a dummy index. That's why you have to put another variable here. So I will write summation over I, summation over j running from 1 to 3 sigma I, sigma j, ai, bj. What are ai? Ai is a number here. Here a is a vector. Eh? So this is the ith component, this is the jth. But sigma I, although it's an ith component of the sigma operator, it's a matrix. Clear? So you cannot write it sigma j, sigma I. Eh? You can put bj, ai. Clear? Okay. So I can write it like this way. I, j is running from 1 to 3. Okay. Okay. So what is sigma I, sigma j? Just we have told. So it is delta ij plus I epsilon ij k. Clear? समझ आओ? Okay, then sigma k ai. So now you are having now. Okay, so take the first term. You sum over j. When you sum over j, this j will be replaced by I. Clear? In the first term. So it will be summation over I running from 1 to 3 ai bi. Okay, then you are having this I, summation over I goes from 1 to 3, summation j goes from 1 to 3, then you are having this epsilon I j k, you are having sigma k ai bj. Clear? Okay, so now what this object is? This is simply your dot product a dot b plus. Now let's look at this thing. So what you are having? So I can put this ai here. So this I can write like this thing. Epsilon I j k ai bj sigma k. Clear? Can I write it? So this gives you the triple dot product. Okay, triple scalar product. This very product. You can expand it. Okay, so let's take I goes from 1 to 3 and then j goes from 1 to 3. It will give you actually the so kth element. Okay, so look here. Okay, so let me give you this thing. So this object will give you. Okay. So how you write the cross product if you don't know? So let's take A cross B. Its ith component. It is given by epsilon I j k. Okay. So this I is here. J k. Then you are having A j B. So while there is a sum over what? J and k. Clear? So this is how we define the cross product. Now what it gives me? So you are having I here, J here. I here, J here. There is a sum over what? I and J. Clear? So समझ आवा? Okay, so there is already sum over K here. So I should put a sum explicitly here. So there is a sum over K, so that you should not get confused. So clear? So now what this object is? This object gives you simply A cross B. It switched the component, kth component. Clear? Okay, if you sum over ij, so this object gives you the kth component of A cross B, then you are having sum over K, this kth component and kth component, it will give you a dot product. Clear? So now if I write, let's say A cross B, okay, like this thing. So let me write C, so it will be something. So this will be, okay, A cross B, its ith component, okay, and Ci. Ith component of this thing and Ci. This is the dot product. Now here you can write as I, let's say Jk, so you can put as epsilon I Jk, Aj, Bk, Ci. Clear? So समझ आओ? Is this the triple dot product now? So it looks like the same thing. So you can put it as simply sigma dot A cross B. So this is a very important identity. So now let me take a corollary here. So if you take, let's say, sigma dot A whole square, like this thing. So that means A is same. So if I take A and B same, what it gives me? Sigma dot A, sigma dot A. What is A cross A then? 0. So what you get? Simply A dot A. So that's equal to magnitude of A. Got it? So this is very important identity. You should know it. Okay. So let's take another identity where I'll use this result. Okay. So now let's take a rotation along arbitrary direction. Let's take the rotation operator along arbitrary direction. Clear? So how I write now? Let me write that as a dm through certain. Okay, so let me write like this. Okay. So rotation through an arbitrary direction, it is simply equal to e raised power minus I. So it will be sigma dot n, like this thing, phi by h cross. Clear? S dot n. So is this a rotation operator now along arbitrary direction? Okay. So can I put it like this thing, e raised power minus I sigma dot n phi by twice h cross? Can I write it? Can I write it? Okay. Now h cross can be. So because s is what? H cross by 2. H cross and h cross will go. Huh? So that means if you are having a spin half particle, you want to rotate it along an arbitrary direction. Clear? Apply this very operator. What I mean by that, you are having a spin half particle described by alpha. Clear? Okay. So this will go as, this will be rotated through which this thing. So this along an arbitrary direction. Clear? So now let's figure out how it looks like. What is the form of this very operator? Okay. Okay. Okay, so let's expand this thing. So you are having e raised power minus I sigma dot n by 2 phi. So let's expand it. I mean, e raised power minus x. So what it will be? E raised power minus I sigma dot n by 2 phi. What will be the next term? Plus minus I phi by 2 sigma dot n whole square. Clear? Then plus 1 by 2 factorial. So 1 by 3 factorial. Let me write minus I phi by 2 sigma dot n whole cube plus 1. Can I write it? Okay. So now let's look here. So you are having 1 minus sigma dot n. Then you are having what? Phi by 2. Clear? So there is an I as well. So I times this thing. Now this is the square of the sigma dot n. Clear? So what is the sigma dot n square? Okay, so let's look here. So you are having sigma dot n square. So what it should give me now? N dot n. So what that is equal to? Identity, because n is a unit vector. Clear? Now let's take sigma dot n whole cube. So it will give me sigma dot n square. Okay, sigma dot n. So what that is equal to? Sigma dot n. So it implies therefore sigma dot n raised power 2n, that's equal to an identity matrix, and sigma dot n raised power 2n plus 1, that means odd. So what that is? Sigma dot n. Clear? Okay. So what it gives you? So minus I square is minus. So you will be getting 1 by 2 factorial. So it is pi by 2 square. Clear? So then you are having plus. Okay. So let's write 1 by 3 factorial. What is minus I cube? Huh? Huh? Minus I or plus I? It's plus I. It's I. Okay. Then you are having sigma dot n cube, that is equal to sigma dot n. So there is actually pi by 2 whole cube. Okay. Minus. Other term will be minus. Okay. Is it? So other term will be actually plus, because that is the fourth power. So I will write it as 1. So this is actually 1 minus 1 by. Okay, it's really not, it's actually an identity matrix, because this is a matrix, this has to be a matrix. So you should categorically put it as a matrix, because I am expanding an e raised power a matrix. So A is a matrix, it is an identity. Clear? Similarly, you will be having here as an identity. So you should put it. So this is actually an identity thing. Okay, so I will put it as 1 minus 1 by 2 factorial, 5 by 2 whole square, okay, plus dash 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 multiplied by an identity. So this identity, clear? Then you take sigma minus I sigma dot n, I will take out. Okay, so what remains inside? It's 5 by 2, then you are having minus 5 by 2 whole cube, 1 by 3 factorial plus dash dash. What is object? It is an identity, cosine of 5 by 2 minus I sigma dot n sine of 5 by 8. So this is an operator. Okay. Fine. So this is the matrix form. Okay, you can write explicitly in terms of the matrix. Clear? Can you write it? Okay, so let me write it explicitly as a matrix. So what is, okay, if I take n is equal to nx, ny and nz, these are the unit vectors along x, y and z direction. What will be sigma dot n? Okay, so it will be sigma x nx plus sigma y ny plus sigma z nz. What that is? What is sigma x? 0, okay, 0, 1, 1, 0. So it will be like this thing. Nz, okay, nx minus I ny, nx plus I ny, then it will be here minus nz. Okay. So now let's use what is identity. It is 1, 0, 0, 1. So put it there. So what you will get? E raised 1 minus I sigma dot n 5 by 2. So that's actually equal to a matrix. Anybody? Can anyone tell me? So you are having the first element will be cos of 5 by 2. What is the first element of the other thing? It's nz, but there is a minus I setting. Clear? So it will be like this thing. Cosine of 5 by 2 minus I nz sine of 5 by 2. Okay, so let's take another thing. So it will be here 0. So it's like this thing, nx minus I and y. So multiplied by minus I. So it will be like this thing. Minus I nx plus ny Okay, sine of phi by 2. So what this will be? It is the conjugate term. So it is I n x plus I n y. Yes. So it is I. Yes, it will be. So sine of phi by 2. So what about this thing? So it is cosine of phi by 2 plus I n z sine of phi by 2. Clear? Got it? So it is simply I am rewriting the matrices. Is this okay? Okay, good. So now if you are having some arbitrary, let's say state, let's think this state arbitrary state. Let's say it is C plus C minus. What that is actually equal to C plus C minus minus. So you can rotate it along arbitrary direction. Just act this object on this column vector. Okay. So you'll get in another column vector. You will see rotated along any arbitrary direction. Then put, let's say if you want along only the z direction, along x direction, along y direction. In that case, let's say if you want along x direction, it will be 1 0 0. You want along z direction, it will be what? 0 0 1. You want along y direction, it is 0 1 0. Got it? समझ रहे हो? Okay. So okay, so let's take this spin, okay, this arbitrary direction. So figure out its eigenstate. Clear? So I will rewrite it. So let's take my n is equal to nx, ny, and nz. Clear? समझ आओ? So what is our s? This operator, it is sx, sy, and sz. So therefore I can write some spin operator s along an arbitrary direction. So that will be simply n dot. Clear? समझ आओ? Okay. So or in other words, I can write this sigma. Okay? Sigma along. Okay. So you can put it in terms of the sigma. What is s? It is h trans by 2 sigma. So it will be simply h trans by 2 n dot sigma. So that is same as h trans by 2 sigma dot. Clear? So this is your spin operator along arbitrary direction. Okay. Now let's check this s square. So what is our s square? So it will be h trans square by 4 sigma dot n square. Clear? So what is the value of this? It's 1. Identity matrix. So it is h trans square by 4 and identity matrix. Clear? So now tell me what are the eigenvalues of this s? So which implies eigenvalues has to what? So eigenvalues are plus minus h trans by 2. So it means the eigenvalues of this very operator are plus minus 1. So in other words, the eigenvalues of this objective are plus minus h trans by 2. Clear? Okay, so now let's figure it out. Okay, and similarly you can calculate what is the trace of s. It will be simply trace of, okay, h trans by 2 sigma dot n. So sigma is having what? So what are the eigenvalues? Plus minus 1. So what will be trace? 0. Clear? Got it? Okay. So now let's write this s. So our operator s, that's equal to h trans by 2 sigma dot n. So how it looks like now? H trans by 2. What is sigma dot n now? No. In terms of the matrix. So it will be nz. Yes? nx minus I and y, what it will be? nx plus I and y, what it is? Minus x. Okay? Now let's use a parameterization. So this is okay in terms of this n's. So if I am having, let's say if I am on the sphere, let's use the spherical polar coordinates, okay? And rewrite these nx, ny and nz. So what is the unit vector on the spherical polar coordinates? Anybody? Okay. So what is our n? Okay. Nx is equal to sine of theta cos of phi. What is ny? So it is sine of theta, sine of phi. What is nz? Simply cos of theta. So it is where? It's a point on a sphere. So it will give the direction. Okay, so this n will give the direction on for a point on the sphere. Clear? So and the components will be like this. Now let's write it. So this operator. So it is h cross by 2. What is nz? Cos of theta. Okay, what is nx? So it is sine of theta. Okay, cos of phi minus I sine of theta sine of phi. Other is sine of theta cos of phi plus I sine of theta sine of phi. Then you are having minus cosine of theta. Clear? So what it will be? It is h cross by 2. So cos of theta will be here. Now look here. Sine theta you can take common. Clear? So what remains? Cos of phi minus I sine phi. That is E. Okay, good. Sine of theta e raised power minus I phi. Then you are having, okay, sine of theta, okay, e raised power I phi minus cos of theta. Clear? Got it? So this is actually a representation of a spin half particle on sphere or in spherical polar coordinates. Clear? The sphere that represents, okay, so if, okay, so let me draw. Okay, so it will be a sphere. Okay, x, y, and z. Clear? So all the points on the sphere. So you can think as a vector. This spin operator as a vector. Clear? And the tip of the vector is on the surface of the sphere. Clear? So Samashiman, the points on the surface of the sphere gives you the tip of the vector. Clear? Samashiman, so it will simply give you the orientation of this s dot n. So this object you can call as s dot n or simply what? Your s operator. Clear? So Samashiman, this representation, this spherical polar coordinate representation of this spin half particle we call as a block sphere representation. Okay? Block sphere representation. Or there is another name for it, what we call as a Poincare, okay, representation. Okay, this is also known as Poincare sphere. Okay, got it? Okay. So you can, let's construct, let's say along z. So this is your theta, and this is your what? Phi. Clear? So this is actually the projection on which plane? X, Y. So it's some, I should say like this. Okay. So this is actually the projection on the x, y plane. Got it? Okay. So now let's figure out the eigenstates of that. Clear? Okay. So you are having the matrix. You know actually what are the eigenvalues. There are